All right, up and running again, full screen. So in this video, I'm going to make a couple of comments about early studies in algebra and how you might, as a student, look at particular problems a little differently. My good friend Yasser mentioned in a comment, I work quickly, and I would like to address that a little bit. Yeah, I do work quickly because it's been my career. I'm familiar with the material. But I'd like to make some comments right now about how you can speed up your work. Everyone can speed up their work with just a little effort, just a little extra effort. In fact, I put on every test, effortless effort takes effort. And it does. So let's take a little effort with one problem, just one problem. Let's look at it a little more deeply. And then maybe it'll save you a lot of work, especially if you become a STEM student, right? And we'll have at it in a second. The other part of the video is I want to talk about point slope form of a line and how I don't necessarily think it's the best way to introduce linear functions at the Algebra 1 level. So we'll have that discussion and hopefully a little bit of a discussion about why it's prominent and maybe its origins. All these things are just guesses on my part. Imogen has given us the word guesstimate, so I'm guesstimating in this in a little bit. But let's start with something we know. Okay, let's start with F equals 9/5 C plus 32. If you don't recognize it right away, it's just a linear function that changes Celsius to Fahrenheit. And we can see that there's a 5:9 ratio. You give me 5 degrees Celsius, I'll convert it to 9 degrees Fahrenheit and tack it on to 32. So I travel overseas to India quite often and hoping to go back and maybe even get to a little closer to Lahore, Yasser. I think we might be heading that direction too. But 5 Celsius cancels, and that's 41 degrees Fahrenheit. And so it's nice if you had multiples of 5, 0, 5, 10, 15, so on and forth. You can do some very quick calculations. Drop a number in, do the conversion, you got a Fahrenheit. So what happens if we manipulate it a little bit? Let's move the 32 to this side. Let's move the Fahrenheit to this side. And then let's multiply by 5. And we get ourselves a new line of work. And if we make the X values or the C values in this case, I'm replicating this, right? We're going to be heading to XY in a moment. Then 9C minus 5F equals 1 minus 160. All right, so effortless effort takes effort. We're looking at something a little more deeply right now. So 9X minus 5Y equals minus 160. It's really what comes out of this. Right, and that's the same thing that we started with over here. And we know the slope over here is 9/5. We know it. We know the slope is 9/5. So can you look at that just the way it's written right now and say, well, geez, how do I get slope 9/5? Seems like you divide by 5 and you change the sign. And that's what I see just by taking a moment. Now, why is that helpful? Well, what if I said typical problem, algebra 1 problem, 3x plus 8y equals 97. Write a parallel line through the point 511. Can we see it over there? Yeah. So what would you write? Well, I hope you would come over here and you drop the 8 and change the sign and say minus 3/8 x minus 5 plus 11. And then if I wanted the perpendicular, I hope you would flip it and change the sign and say 8/3 times x minus 5 plus 11. And I said, take a little time and look at your answer and look what you started with. Oh, perpendicular, 8 divided by 3. Now, as an instructor, that's helpful for me to know because if I'm correcting papers all day long and I'm working with the material, it's nice to know what the slope is immediately. It's nice to know what the perpendicular is immediately from standard form. What did it take? Yes, at this stage, that's effortless for me because I've seen it so much. And it took effort, some effort to make that happen. I'm suggesting you do that with most every problem you do. Do the work, If you understand it, take your last line of work, the answer to whatever you started with, put it in front of the original statement, see if you can make a connection and speed up your work. There's nothing wrong with that, I don't think. All right, so I hope that's just a little helpful suggestion as you move through your high school careers, or a lot of people looking at this now who are up there in age with me, and I'm delighted by that. God, it's so nice to be talking to some folks and meeting people different places and hearing people are doing some work again in mathematics. All good as far as I'm concerned. So now I want to talk about point slope. I got Freddie the card here, Renee the card. Now I'm getting forgetful. So let's go, Renee. Let's go down this way and have a little chat about point slope. All right. So here we are. Nothing rehearsed here, just off the cuff commentary. So point slope, y minus 10 equals 2 times x minus 10. Trying to keep the numbers as simple as possible here. And base 10 is a nice number. 10 is a nice number to work with. So I decided to do that. So we could change that to 2x minus y equals 10. And that's a minus 1, right? If you change the sign, you got a 2 over 1, which is the slope, just to repeat. The other thing I put on my tests and worksheets is repetition is our friend. Came from a Tai Chi master. And I think he's right. And effortless effort takes effort. Came from a very well-known spiritual gentleman. And I think he's right. All right. So if we move if we change the signs, make that negative and move it to the other side, then we've got a positive. And I just changed the signs of everything. So you got your slope intercept form, which is kind of a put a number in, do the math, get an answer. Okay. You put a number in point slope, you still got to do another calculation over here. Yeah, it's quick and easy, right? But it's still another little synapse from the neurons. And if you want to speed up your work, it's nice if you cut that down. And I think moving the minus 10 to the other side, we start, and I think that's what happened with f of x notation. I think somebody said, we read left to right. So you put a number in, you do the calculation, you get a number out. That's not the case with point slope. You got to put a number in, do the calculation, and then slightly another calculation, 0 is equal 0. Again, we're not talking rocket science, but it's still another synapse. Okay. So I'm a big fan of this, right? And I'm hoping that you can see that this fits the 2x minus h plus k format. All right. But each of these tells us something. This tells us 10, 10 is on the graph. I didn't graph it over here, right? Because standard form tells us what the x and y intercepts are. So x is 5. We can see that. We cover this up with a 0. Y is negative 10. That's good. We can see a rise of 10 units and a run of 5. All right. So we're looking at a 2-to-1 ratio. So it gives us useful information. I think slope intercept probably came about because it's the easiest thing to work with is multiplication by 0, giving you a y-intercept of negative 10. Okay. So yeah, it was easy to work with. So people teach it. And that's fine. Nothing wrong with that. Everything has its place. But I think this is the most useful. I think this is definitely the most useful. Patterns start from HK. I put that down somewhere else. Making notes to myself. Where did I put it? I guess I put it here. So let's actually move this down just for a minute. Sorry for the movement here. But yeah. So, we've got point slope. Right. And but if we move the k, I think we can see HK, which is a location. And most functions have patterns that we study. The initial ones. Where did I put it? Oh, up top here. I mean, you've got a circle. Oh, HK, center of the circle. Circle. The pattern emanates from the center. Vertex of a quadratic, HK, right? Point of inflection of a cubic, HK, and they fit these graphing forms, right? Which can be extended then, say, to the 4th degree, so on and so forth. And that just doesn't stop. And we were looking in a previous video. I'm getting off topic, so let me just go back to this over here. So Yeah, I think this is the best form if we write it as a single term. Right? Using multiplication, writing that as a single term, we get minus b over a, which is where a linear function changes signs from positive to negative or negative to positive. In the vertex form of a quadratic, HK obviously stands for where the pattern emanates from. Right? We just talked about that briefly. So what do we do in math? We start with an input. We start with some value, we call it X. We need a frame of reference, and Descartes gave us these measuring sticks, rulers, superimposed on each other. And our eyesight basically goes to the center, right? When we put an XY axis in, we look at the center, and we're able to measure inputs are random. We pick an input. It's nice to put the number 1 down. It also gives us a sense of guesstimating. All right, and we call it the x-axis. But what do we work with, say, if I want to write a linear function and I start with x equals 5? Well, we generally start by saying x minus 5. Okay, so what does that tell me? That this x-axis just got 5 units shorter. I'm just taking 5 units away. And now I'm really measuring from a new perspective. I'm measuring from 5. So I'm going to take these 5 units away. I'm not working with the negative numbers right now. I'm just shortening that axis, which means that when I plug a number 6 in, I've got 1 unit of change. Now, the other way to think about x minus 5, we could have drawn a linear component right through it. And when I get to 6, I get 1 unit of change, but it's shown vertically. Okay. So that's what the x-axis looks like. This is what the x minus 5 axis looks like. And I still think there's room to be playing with different names for different axes, because I think that's where the chain rule comes from in calculus. But that's for another time and another place. So we could do the same thing with the y-axis. We could say y minus 5. Take away 5 units. And if we did that, well, we really have a new frame of reference. So this is the axis x minus 5, and this is the axis y minus 5. And the pattern seemed to emanate from 5, 5. So let's see what we can do with that. Come on. You're following this. Good for you. Feel like I'm rambling. But I have something I want to share. It's a little awkward. A lot of the stuff that I'm putting out there, I haven't practiced talking about a whole lot. But let's see if you can follow where I'm going. So here's a typical problem that in Algebra 1 we're covering it, in Algebra 2 we're covering it. It's a Pythagorean relationship, where I have x minus 5 squared plus y minus 5 squared equals 25. Let's dive into it a little more deeply. Okay. And it's very similar to the standard form, 2x plus y equals 20. I'm seeing something plus something equals a constant, right? How do we work with this? We work with this with zeros. Y could be 20 or 2x could be 20. And get some data quickly. Well, this could be 0 if I put a 5 in. There's no change. There's x minus 5. I put a 5 in. I haven't moved it all. Everything would have to come from this equation. And if I let y equal 5, no contribution to the process. And what are you seeing? Well, hope you're seeing the Pythagorean relationship. X minus 5 squared is the area. If this length was, that axis is the x minus 5 axis, right? Then this is x minus 5 squared. This is the y. That's got to be 5, right? And hopefully you can see the y minus 5, the square root, right? So that's really what we're looking at. And when you square things, 0 is the smallest thing you can square, right? That's it. That's a minimum value. Generally speaking, you've got a positive plus a positive equaling a positive in the Pythagorean relationship. The sum of the squares of the smaller sides of a square area equals the square area of the largest side, something like that. Ask the scarecrow. Scarecrow's got it down pretty good, I think. Yep, does this kind of thing. I don't know, scarecrow. All right, so y can't be greater than 10. 10 minus 5, 5. 5 squared, 25. I can't add anything to that. So I can't pick a number bigger than 10. So there's restrictions here. Same thing is true of X. So we've got some domain and range issues to talk about. But what we were looking at was measurements. And so what happens if I went to 8? Well, if I went to 8, then that's 3 units. What's the contribution? I need the number 9, I need 4, right, to make a triangle. I need 4 units to get 5. 9 plus 16 equals 25 in this right triangle. I have a place that satisfies the conditions set forth in this statement. The next value of 8 makes this 3 squared, a y value of 9 makes that 4 squared, and I think that's 5 squared. 9 plus 16 equals 25. And what do I have? I've got shortened axes. Okay, that's fine. What else could work? Well, could have been 4 here. 4 squared, and that's 3 squared. Okay, so if I move 4 units, then 9. Let me erase this picture, except that dot's there. Now I have not 8. I go over this way 1 more, so now it's 4. That area gets bigger. This area has to get smaller, right? That's got to be 3. Right? So 5 plus 4, that's 9. 5 plus 3 is 8. And now, oops, I wrote the wrong number. Now I have a new coordinate, and that new coordinate is 9, 8. Well, I could keep doing that until I get to what on this axis? Till I get to the number 10. When I get to 10, I can't have any contribution. 10 minus 5, 5 squared, 25. This has got to be 5, which is where we were measuring from. So I'm here. I hope we can begin to see, and I will do a negative now. I will do a negative. What if I put a 2 in here? 2 minus 5, negative 3 squared. Well, there's my 9. This could still be 8. No, I got to, what do I need here? I got 9. That's got to be 4 coming out of this. So positive 1. Okay, positive 1 is down here somewhere. I hope I located that properly. But what I'm looking at here is the rotation of a circle, rotator cuff problems, but that's my new origin. So point slope, say y minus 5 equals 2 times x minus 5. I think get prominence because we're looking at new measuring sticks. New rulers, where they're placed to see where patterns emanate from. All right, so I'm not a big fan of point slope, but I think that's probably where it came from. All right, so you know, if that generates some little thought about what's going on here, then all well and good. All right, so I am going to post that. It was a little awkward, but I think the topics are important to think about. All right, have a good day.